from space, both highlighted uncovering knowledge into the insider facts of the early universe, as stargazers transparently gave vast hours to filtering isolated patches of the sky, searching for ahead-of-schedule universe inestimable frameworks. They initially expected unassuming disclosures like a more detailed variation of the Hubble Deep Field. Regardless, they were in for a shock. Stephen Finlin from the School of Texas at Austin, leading the SE project, figures out that exceptionally distant frameworks should emerge exclusively later. Various data cycles from unique projects anyway, to cosmologists' wonder, showed these universes appeared rapidly. Beforehand, the record for the most far-off realized framework had a spot with GNZ 11, seen in 2015 with a redshift of 11. Redshift gauges the stretching of light due to the universe's expansion, with a higher value exhibiting more remarkable distance. Yet, from the very start of glass observations, two separate groups, including one led by Rohan Natu, openly recognized glass Z13 with a redshift of 13, driving the huge plan back significantly further in their scramble for swift results. Experts relied upon improved methods for redshift evaluation in view of wonder assessments as compared to extra time-intensive direct assessments. Regardless of their ease, these assessments revealed worlds out of nowhere, splendid, giant, and tremendous, some already parading a magnificent man rising to a billion children, similarly as our own smooth way, which is billions of years more encountered. The energy didn't stop there. In the subsequent days, various universe contenders from Sears and Glass emerged, some with redshift checks as high as 20, showing they existed just a brief time after the Big Bang. These universes showed spiral-like plans not expected in such early cosmic ages. Moreover, another group tracked down confirmation of smooth squander frameworks at a redshift of 10, under 500 million years after the Big Bang. Such a quick ascent of sizable universes challenges the assumptions for the standard cosmological model, lambda cold dark matter. To get a handle on this oddity, a brief revisitation of early universe components is essential. In the fundamental minutes after the Big Bang, the universe was a hot, thick soup of early-stage particles. Over the long haul, as the universe expanded and cooled, helium and other light elements formed, provoking the presence of the first particles. About 400,000 years after the Big Bang, conditions became conducive for the formation of the first stars made mostly out of hydrogen and helium. These early stars, larger and more mind-blowing than current stars, accumulated into protogalaxies, organized by the gravitational pull of dark matter. However, JWST's discovery challenges this model as it uncovers incredible, sizable vast frameworks far sooner than expected. Stacy McCor from Case Western Reserve University observed the frightening shortage of different, more unassuming protogalactic parts, suggesting that some seen frameworks may be closer than accepted, concealed by dust, appearing dimmer and more distant. The revelation of the early universes raises significant issues about the universe's beginning stages, highlighting the need for continued examination and revision of our cosmological models. Follow-up insights of glass Z13 in August 2022 by the Atacama Large Millimeter/Submillimeter Array ALMA cast doubt on the initial revelations. Despite the use of splendor-based assessments, ALMA didn't detect significant amounts of buildup related to glass Z13, as P. Tom B. from Goya School, who led the insights, noted. This suggests that low redshift gatecrashers can be ruled out. However, ALMA attempted to detect the universe using all possible means. This highlights the trial of confirming insights made using JWST's high capabilities. Rohan Natu, one of the experts involved, raised the incoherency of the situation, stating, "The good news is there's nothing new." He said, "The bad news is there's nothing related to just JWST. It's fit for returning to its own insights." The most terrifying explanation could be that the standard lambda cold dark matter cosmological model requires updating. Michael Bohan Cullen, a cosmologist, conveyed the size of this likely change in perspective, communicating that these results are incredibly shocking and hard to reconcile with our standard model of cosmology. It would be a real upheaval to understand the quandary. One problematic recommendation is to alter Newtonian components, challenging the presence of dark matter. JWST insights could support MZ, proposed by Mark McCarran. However, not all cosmologists are convinced of MZ's legitimacy. Another possible clarification is that early universes could have minimal buildup, making them appear more substantial and affecting mass calculations. The situation could also explain ALMA's difficulty in detecting glass Z13. Charlotte Brickley and her partners suggested that JWST could be seeing the most stunning, energetic frameworks in the early universe, which could indicate simpler star formation conditions during that age. David Spergel supports this idea, suggesting that high-mass star development might have been more efficient due to higher gas pressures and temperatures, possibly influenced by early magnetic fields. The rapid dissemination of JWST's initial discoveries reflects a shift towards continuous peer review through stages like A14 in social media. While this accelerates the dissemination of discoveries, there are concerns about rushing conclusions before thorough peer review, potential recalibrations, and the fact that all makes hardly any results. It's improbable that all high-redshift massive frameworks seen by JWST will be invalidated. The sheer number of these universes suggests that the early universe may be different from what was previously expected. Fin Lin expressed confidence in the validity of the revelations, communicating that the chances of cosmologists being entirely wrong are small. Currently, stargazers are rushing to coordinate subsequent insights with JWST. Nancy Levinson is now assessing around 12 proposals from various teams, seeking additional JWST observing time to examine high-redshift infinite framework newcomers. Given the excitement and importance of these early revelations, confirming them is crucial. One of the proposals highlighted the importance of verifying these discoveries. Unique projects like Universe Webb, led by Cartel T, aim to expand the known population of early frameworks by observing a more extensive region of the sky for several hours. They estimated that they could identify many more frameworks. Additional efforts will search for confirmation of the first proto-universes, possibly using the remains of very early stars and supernovae as markers for their existence. Some estimates suggest that JWST could detect supermassive frameworks up to a redshift of 26, just a brief time after the Big Bang. Confirming even a small number of these high redshift newcomers would be a remarkable achievement, as indicated by Natu, demonstrating that cosmologists are not being misled by their observations. JWST has ushered in a new era of science, and despite its weaknesses, the rapid communication of new revelations has invigorated stargazers with excitement about the robust scholarly community. The question now is whether this is the right time to reconsider how we interpret the earliest beginnings. The significant repercussions of exploring the early universe's unknown world are clear. For now, make sure to show your support by purchasing and sharing waves in and out of town for future episodes. Also, be sure to share your thoughts on the current content. Your support inspires us to continue delivering quality content and to strive for continuous improvement. Appreciation for watching, and we'll see you next time. In conclusion, the James Webb Space Telescope, JWST, has ushered in a new era of investigation and discovery, testing how we might interpret the universe's origins and evolution. Its extraordinary observations of universes formed shortly after the Big Bang have sparked excitement and debate among researchers, pushing the boundaries of cosmological knowledge. The telescope's ability to peer further into space and time than ever before has revealed astronomical phenomena that challenge conventional models, leading to a reassessment of existing theories and the formulation of new ones. From ancient galaxies to the mysteries of dark matter and early star formation, JWST's discoveries have profound implications for our understanding of cosmic history. Looking forward, JWST promises to continue unraveling the universe's complexities, offering glimpses into realms beyond our reach. Its revelations not only advance scientific inquiry, but also inspire wonder and curiosity about the universe's vastness and our place within it. As JWST embarks on its mission to explore the cosmos, scientists eagerly anticipate the new discoveries that lie ahead. With each observation, we move closer to answering fundamental questions about existence and gaining a deeper appreciation for the cosmic tapestry that surrounds us. The James Webb Space Telescope stands as a testament to human curiosity and ingenuity, driving us toward a more profound understanding of our cosmic origins and our place in the universe's grand narrative. The theory of the Big Bang is widely accepted by most scientists as the primary explanation for the universe's origins, encompassing the creation of stars, planets, and all life. including us. Despite its somewhat dramatic name, the term Big Bang accurately conveys the enormity of the event. Initially, the universe was a dense array of particles compressed into a space smaller than a pinhead. From this point, a massive explosion of matter occurred, known as the Big Bang. This succinctly summarizes the process that unfolded over billions of years. However, despite the enduring popularity of the theory, advances in scientific data have increasingly challenged its predictions. When NASA launched the James Webb Space Telescope, the largest and most advanced space observatory to date, experts speculated that its observations would support the theory of the Big Bang. Unfortunately, after just 1 year in space, the telescope has baffled scientists with its pivotal findings, providing unprecedented glimpses into the universe's past. The James Webb Telescope's revelations have exposed galaxies so old that they could fundamentally reshape our understanding of the universe's origins. This surprising discovery has generated significant interest among both scientists and enthusiasts. One notable revelation came when astronomer Rohan Natu, examining early images from the James Webb Telescope, unexpectedly identified a galaxy that astonished everyone. This galaxy, named Glass Z13, appeared unusually large and traced back to shortly after the Big Bang, making it older than any previously observed galaxy. Nata's excitement was palpable as he shared the discovery with colleagues, describing it as beyond what astronomers could have imagined. The James Webb Telescope, positioned far from conventional interference and equipped with cutting-edge technology, was designed to delve into the universe's earliest era, known as the Cosmic Dawn. This period, shrouded in mystery, marks the formation of the universe's first stars and galaxies. By studying galaxies from this epoch, scientists hoped to refine our understanding of fundamental cosmic processes, such as the impact of matter and dark energy. Initial expectations for the James Webb Telescope's discoveries were modest, anticipating a few faint, distant galaxies. However, reality surpassed all projections. The telescope's images revealed galaxies of astonishing development, challenging existing models and sparking a whirlwind of analysis. As researchers continue to analyze the James Webb Telescope's data, the implications of these discoveries could be profound, ushering in a new era of cosmological understanding. The remarkable exposures from this significant observatory offer an intriguing glimpse into the universe's past, driving humanity's quest to unravel the mysteries of existence. As early galaxies emerged, researchers and observers found themselves in a race to understand them. Could this collection of unusually large and bright early galaxies be an anomaly, perhaps due to inaccuracies in the telescope's initial data? Or, if real, could they somehow fit within conventional cosmological models? Perhaps they indicate that the universe is more peculiar and complex than previously imagined. The challenge lies in deciphering how the universe we know emerged from primordial chaos. The early revelations from the James Webb Space Telescope may potentially revise our understanding of cosmic history. These findings not only concern distant epochs and galaxies but also our own existence here in the present universe. As Mark McCarran, a senior advisor for science and research at the European Space Agency involved with JWST, remarked, "You build these machines not to confirm the perspective but to break it. You just don't know how it will break." The JWST's observations of early universes have been billions of years in the making. More subtly, they trace back to the Space Telescope Science Institute in 1985. At that time, the Hubble Space Telescope was still years away from launch. However, the Institute's then-director, Ricardo Juan, urged his team to consider what might come after Hubble, despite initial debates about focusing on Hubble. Juan was insistent, foreseeing the extensive development process. Fellow Waite, then deputy administrator of SD-Sky, along with a small team, began drafting ideas for what eventually became the James Webb Space Telescope, later renamed JWST. They recognized that while Hubble would be groundbreaking, its capabilities would be limited by its observations in visible light. The JWST, on the other hand, would operate in the infrared range, allowing it to peer further into the universe. The need for JWST became even more apparent in December 1995, when astronomers conducted the Hubble Deep Field observation. Contrary to expectations of finding only a few faint galaxies, the resulting image revealed a vast number of galaxies extending back more than 12 billion years into the universe's history. After over 20 years of development and at a cost of approximately $1 billion, JWST finally launched on Christmas Day 2021. The telescope underwent rigorous testing before reaching its intended space position a month later. By July 2022, it was ready to commence its long-awaited first year of scientific observations, known as Cycle 1. Some of JWST's initial mission was dedicated to high-impact programs, including the Space Traveler's Micro-Advancement, Early Release Science Survey, and the